Okay. So are you guys able to see the screen?
Yes.
Okay, fine. So today, like, we are going to see about peer-to-peer systems. Like, I'm sure, like, most would have known about peer-to-peer systems. For example, BitTorrent. So generally, let's start by defining what is P2P. Like, what is peer-to-peer system? P2P is basically a decentralized thing where no particular entity is marked as a server or something which with higher priority or something. It's just a bunch of nodes with the same, let's say, a same uh, work to do. Yeah, that's it. And there, it is fault tolerant and highly scalable thing. Uh, Basically, we can't say P2P is entirely just a storage system. It could be anything. Like it could be in this example, we are going to look at P2P, which could be act as a web service. Like we are going to look onto different P2P systems. Then how could they be used as a web servers, something like that. Uh, so the characteristics, let's say what functionalities in the of the system we are going to see. We're going to see about how to bootstrap a particular node into the system. Then how we are going to see how to place the data. Like let's say we have a music file and where to place it and how to get that file. Then routing. So since our internet is not made for P2P, P2P is more of a hacky thing in this internet system. We need to see how they are going to route the request inside the system and fault tolerant. Say, let's say one node goes then how the entire system is going to be working. Since P2P has a high rate of churning, like nodes could be leaving, like many number of nodes could be leaving and joining. Whereas in real case scenario, let's say we have a web server, there is not we won't be seeing high number of churns. So following on the P2P systems we are going to see today. So Napster, Nutella, Cord, and Calypso. So let's start with Napster. To say like Napster or Nutella are more of let's say it's not a really academic based things. No, Napster and Nutella are more of let's say practically implemented thing, and they are not academically well researched or something. Whereas Cord and Calypso are well researched or academic. They are much structured compared to Napster and Nutella. So let me start with Napster. So like Napster, you have known about Napster. It was just a peer-to-peer file storage system, but eventually converted to music sharing platform. So if you have seen that, uh, like the social network film, you would have known about Napster. Well, it has been brought down because of a copyright infringement. I mean, not copyright infringement directly. Like it is giving a chance to do copyright infringement. So that's why. So let's see how the Napster works. Napster, let's say these are the peers, like peers, or just nodes which uses the Napster, and there is basically some server which acts as a service discovery, which acts for service discovery, and it will be owned. For example, if say Napster, then www.napster.com or something like. If you want to create our own thing, let's say www.paroscale.com or something paroscale.in, their DNS records will be mapped to these servers, and the files we can upload our own files. Like we won't be uploading it to the server, we'd be just having our own files in our node itself. Let's say this is our node, this p1 is our node, and we'll be basically having all the files we want to share. In this case, as I said, we are going to look at web service example. We host something like sample.com, something like a sample.com, and a few other websites like v1.com or something like that. Basically what we'll do when we join the system, and we will say like I'm having following resources and my IP address is this. So the server will store a tuple entry saying this particular service.com is stored by the following P1 address. It will have a tuple, like it will be replicated among these servers or say for fault tolerant purposes. So it creates a tuple. It basically creates a tuple of tuple where the particular service lies or particular thing lies, something like that. And v1.com and again P1 address, something like that. And again, if sample.com is repeated in multiple peers, let's say multiple peers provide the same website. In this case, sample again, the sample.com, it will have multiple entries, P1 address, P2 address, and let's say what are the node which provides service.com thing. And now this particular peer, let's say PN, requests the server for service.com thing. So it sends the data like I want to get the files of sorry, just sample.com or service.com. Okay, just have it as service.com. Let's say it sends a request for service.com to this server, uh, service.com. So it will this particular node, when it's sent to a server will search through its record, its lookup data, and it finds which particular node hosts those address. I mean, hosts those servers. Let's say we P1 and P2 host those servers. It will return the data with P1 address and P2 address. P1 address and P2 address will be returned to this particular PN, and the PN in turn will be trying to connect to the P1 and P2. Like depending on which particular node it could communicate fast, round trip time is very less. It will connect to that node and get the data. So this is how Napster works. And as you could see, it's not completely decentralized. There is still the presence of server for lookup things. So it's not completely. I mean, it defeats the purpose of decentralization, and moreover, it's really easy to take down if you just remove the servers. I mean, to take down these servers, and the NAPS and the particular P2P service won't work. So that's it. So here, then the next, let's look into the next P2P system, that is Nutella. Like Nutella is a completely decentralized P2P. It doesn't have any servers or anything. Every peer acts as a file sharer, and that's it. No servers or anything. And they form a overlay network among them. Like overlay means, let's say, underlying network could be any type. Like underlying is internet. They form a overlay. It's more like an application level routing. Let's say. Uh, so they form a mesh kind of network. They connect with neighbors or something. Uh, so they connect with the neighbors. Let's say how we could implement a web service. Like at last we have seen how they implement web service in Napster. Let's see how we could implement a web service in Nutella. So Nutella usually have four type of, I mean, let's say four type of messages: ping and pong for heartbeats to get to know whether a particular neighbor is alive or not, and a query. Query is just like querying a particular file, querying for a particular service or something. And query hit is basically, let's say, I'm trying to search a particular thing, particular service, and if a node has that particular the service I'm requesting for, it sends back a query hit message. And push and pull is just to get the data, something like that. I will describe about push and pull later. So messages in Nutella contains following thing: message IDs. Whenever they generate any type of message, they have message IDs, and message type, depending on what type it is, and payload, and the TTL. So message ID is just used for duplication, like to avoid duplication of request. And since Nutella uses flooding of requests, like when I send it to a particular node, it floods to all the neighbors it has. So to avoid the duplication, since there could be redundant links or redundant way to reach a particular node from one node, then there could be a chance of duplication. So to avoid that, we use message IDs. And message types, as I said, what type of particular message. I mean, if it is a ping or POG, query hit or push or pull. Payload. So payload, depending on the data, depending on a message type, we use the payload. Then TTL is used to avoid forward to message to regulate. Like since it uses flooding, we need to regulate at some time to avoid message to go beyond. Let's say we don't want to make the message keep on routing in the same in the network. It will let's say it will consume more bandwidth, or it will just stall the network. So to avoid that, we use TTL. TTL is just a time to live, or more like a hops. Like if I say TTL is 2, then if it sends to a neighbor, it will decrement the TTL until the TTL is 0. It will be forwarding. Once the TTL is 0, the particular node will discard the packet, and let's say leave it. Let's look into an example. So in this case, let's say this P1 is the node which, let's say I will mark the P2, P3. P4 and P5. So P1 wants P5 hosts this service.com or something. Let's say this service.com, and P1 is trying to find the service.com. So it wants to access the service.com thing. So what it does, it creates a message like with query with TTL as type message type with this thing. And so let me draw it. Message ID. Message ID, then message type and payload and TTL. Sorry if my handwriting is better. It's just difficult. Just message ID could be like, let's say, identifier for a particular message. It should be unique for all the message creates. Something like P1, P1 underscore 1, so that it will be unique. Like if we include the node address, node identifier as well. Message type could be query or query, and payload could be service.com in this case. And TTL, it could be random. Let's say if TTL2 it's not able to get the request, it could increase to TTL3. And like if it want to increase, then it could increase TTL. Let's say in this case, TTL is 2. It forms this packet, and it sends to its neighbors. So this packet is sent to P4 and P2. So what it does is P4 has a routing table, and every node has a routing table. So what it does, it will look into the packet, and it will say whether it is able to find a particular service.com in its own, like whether it hosts service.com. If not, it forwards. So forwarding, what it does is creates a table. It has a table where message ID from where it received, sending node. So something like that it creates. So it will, this particular message ID is P1 underscore 1, and the sending node is P1. So it has this, it stores this particular tuple in its memory. And same way the P2 also stores. Same way the same routing table is stored in P2 as well. So let's say the P4 sends the packet to P5 first, then P2. And what does P2 does? It searches for, whether it checks whether it hosts service.com. Before sending to P5, what it does is, it uses the same, it forwards the same packet, but now the sending address will be P4 instead of P1. So the P5 will just will know only it is sent by P4. It will abstract the idea of P1 sending it, more like a proxy. P4 acts as a proxy to P1. So when P5 receives the message, it checks whether it hosts service.com. If so, what it does, then it just say query hit. It creates a new message. Let's say in this case, query hit with same identifier as P1. Whatever the query, same identifier will be used, P1 underscore 1 in this case, and service.com, and let's say query hit and its own address, P5's address will be here. So that's it, P5 address will be here, so that it could connect then. And this particular packet is framed, and whenever, so it routes back to the node which sends its address, which actually forwarded to query message to it. So it sends back to P4. So when P4 receives this particular packet, it checks its routing table. Since it's a query hit, it checks the ID, message ID. So if the message ID is present in its routing table, it will check P1 underscore 1 as present, and I have to forward it to P1. and it sends back the query hit message to P1. Query hit to P1. And the P1, when receiving the query hit, it will get to know the P5's address, so which hosts the service.com, and it will, in turn, it will make the connection to P5 directly. So it will connect with P5 directly and get the data. So whatever the, let's say service.com is a website, it sends HTTP request and gets the data. So this is how Nutella works. And let's say if you want to add, like, let's say you want to connect to the existing network, existing Nutella network or something. Let's say you have made some Nutella network and your friend wants to connect to the particular Nutella network. What he can do is he can just ask for your address. Let's say your Nutella address, your node's address. Let's say this you. You can provide provide him your address, and let's say PN. Using this address, he can connect with you and he can establish you as a neighbor and send a ping pong request, like ping request. Let's say he sends a ping request to you, and in turn you forward the ping request to other nodes. Like depending on TTL, it will be forward to other nodes. On receiving a pong request, on receiving pong, it could connect with them. It could connect with them. So let's say in this case P5, you send a ping request, and in turn the ping is forwarded to others who are all the neighbors, and ping is with 2. I mean, TTL is 2, so it will only forward to the next thing, and the P5 will reply with a pong, and P1 will also be replying with a pong, and they will maintain a. In turn, if PN wants to connect with P5 or P1, depending on its let's say policy or something conditions. Okay, if I want to connect, it could connect. If not, they don't want to connect. Let's say it just wants to connect with P5, it could establish a connection with P5. So something like that. That's how they get bootstrapped into the service. So any doubt regarding the Nutella? Hello? Can I continue?
Yes.
Okay. So problem in Nutella, like let's say what's the problem in Nutella? Yeah, it's still a good P2P. Like it is completely decentralized and it's able to do what is required to do. But two issues is poor load balancing and order of n routing. Like it's not really scalable because let's say only the problem of P2P is there could be leeches. Like they won't be hosting any files, but they could be using the system, and a particular node could host all the number of files. So there is a poor load balancing thing. So this happens. Then O of n routing. O of n routing, and since Nutella doesn't restrict a particular node from having any number of neighbors, or it could not restrict how the overlay network could be formed. That's the chance that a network could be formed as a single linked list, like a singly linked thing, something like this. Network could be formed something like this, and the first node queries for the data which is present in the last node. So this is basically like a O of n routing. Like it has to go to till the last, and the response has to be received from the last node. Query and query hit must be received from the last. So this is what happens. Like this is why they introduced a structured P2P version from academia, like which could have a better routing and better load balancing. Now we are getting into the core thing. So core is more of a structured P2P system where they arrange in a circular fashion. And we do find like each node has a ID. Like let's say ID, how we get the ID is using a consistent hashing thing. We use their IP address, like PS IP address and port is passed through a hash function. And hash, when let's say we use SHA 128 or something which outputs SHA 1, or no, SHA 1, it outputs 128 bits, and we can truncate it to m bits. So m bits is basically like expected total number of nodes in a system. Let's say we expect only around 256, maximum of 256 nodes at a time, and usually it has to be higher than maximum expected. because to avoid collision, let's say, I mean, there could be a chance that two hash could be colliding, and in turn, it has to rename the particular node's ID. So we'll be truncating from 182 to m bits. Let's say in this case 8 bits. So we can totally have only from 0 to, I mean, totally 256 nodes in the system. 256 nodes, and their ID could be mapped from 0 to 255. So each node will have their own ID. It doesn't mean every time the system has to only has to have 255. I mean 256 nodes all the time. It could have one. It could have two. It could have 255. Like within that range, it could have in the system. So that's how. And even the key, let's say in our case, we are using web services. Even our web services name could be hashed. Let's say if you use service.com, we don't want to use the same header, the namespace which is used in the internetservices.com or something. We can use our own naming thing. But for easily understanding, I'm using the same namespaces used in our web namespaces used in our internet thing. So again, in this case, what we'll do is service.com will be, oh, sorry. So service.com, let's say if we have service.com, it will be hashed, and we'll be truncating it to, let's say, I mean, however we want here. I'm sorry, not however we want, sorry, my bad. We will be truncating it to m bits, and we'll be finding the ID. So it will provide a particular ID. Using that, we'll be routing the request to the node. So let me explain the routing later. So for now, this is how the hashing thing works, like finding identifier of a node or a file or or a data will be done using this, not data, let's say, meta of a data will be done using this thing. The hashing thing has to be same in all the nodes. Like in a particular system, they has to be same. Like if nodes are in a system, they have to use the same hash function. No matter where you hash a particular data, same data must provide a same ID in any node. So that's what the constraint. So the consistent hashing, as I said earlier, this consistent hashing, like what you mean by consistent hashing? We have used hashing data structure in normal programming. Hashing data structure usually maps a particular index to particular data. So we hash a particular data and we mod it to total number of spaces we have. Like usually the pigeon hole thing we used to say. In Max, they used to say pigeon hole. So same way we hash a data and map it to a particular index. What if we have more amount of data? Like what if you want to increase the number of bins, then we have to do is we want to restructure the bins. Like the data will be remapped to every node. But when you use consistent hashing, we basically just limit the number of bins we have. Like we won't increase the bin. The bins will be decided at the first, no matter what we change. It won't be increased. But if you remove a particular bin, the data remapped will be very less. Removed means the total number won't be reduced. Like you will be using the same hash function and same mod. You won't be changing the hashing thing, but only the data will be remapped. So it will be going to the next thing. So to provide you an example, let's say that could I draw this? Okay, let me explain it later. Let me start going to the routing thing. So routing so let's take this particular code system into example to understand the routing. So we have totally we assign m equal to 8. So totally 256 thing. 256 node could be present, and IDs could be ranging from 0 to 255. Since as I said, every node need not to be present in the system every time. There could be few nodes, and now it's just these 6 nodes are present in the system. So as each node has the data about its successor and other node, like few other nodes. Few other node means it uses a finger table entry. So finger table is basically like it stores the information of few nodes. Let's see how the finger table is populated. So the finger table has a number of it has m entry. So each node maintain its own finger table. So each finger table has m entries depending on the system. Let's say here m is 8. So each node has 8 entries, something like that. It has its own finger table, ft10, let's say ft50, ft128, ft200, and FT250 or something like. So each maintains its own finger table. So how the particular finger table is populated. So this is the formula here. So we use this particular formula to populate the finger table. So what it does, so let's say, let me use entry ft of I. So for 0th entry of finger table, it's basically the node ID. So we use this particular thing, node ID plus 2 power I and mod of n. So mod of n means it's just 2 power m. So 2 power m, this is how we use. So here, so let me substitute this I is 0 here. If you substitute for, I'm considering this particular table entry for, let's see, let me use a different color. Let me. So I entry equal to node ID plus 2 power I mod of 2 power m, and use the ith entry and the ft of I. And for this is for node 10. So this finger table entry of node 10. So for 0, it is just 10 plus 0, 10 plus 2 power 0 mod 2 power m. So 2 power 0 is 1. So 11 mod 2 power m is here 256. So 11 mod 256 is 11. But since the 11 node is not, the 11th ID is not present, like we don't have a 11th ID node, we use the successor, like whatever, let's say in the space from 11 to 49, whenever we get ID from 11 to 49, it will be mapped to P50. So whatever the successor present, these node will be mapped to 50. And same way from 51 to 127, this will be mapped to 128. So basically you get the idea, right? So we map whatever the, like if the space, if the particular ID, we don't have a particular node for that ID, then we map it to the successor. Since we get the 11, since the 11th node is not present here, will be mapped to 50. And same way, if you do for next entry, ith entry, 1, we'll be having till 7. So 1, if you do 7, 1, oh, 1, it's basically 10 plus 2, 2 more 256. It's 12 more 256. And it's still 12, it will be 12. And since still we don't have 12 node, it will be mapped to 50. And for 2, it's, let's say 2, let me use a calculator for this. 4 and it's 14, and again it's 53, 3, so 8, and again it will be a 54, let's say 4, 4, 2, 4, so 16, and 16 it will be still 50, and 5, 16 into 232, it will be like 42, and again it's still 50. For 6, it will say 64. It will be 64 plus 10. 64 plus 10 will be 74. Since the 74 for 74 thing is not present here, it will be mapped to 128. And for 7, it will be 64, 128, 138. Since 138 node is not present, the successor, the next best thing is 200. So it will be mapped to 200. It will be the finger table entry for the 10th node. So the storage, we store log n nodes, log n nodes. So that is m entries. So total number of nodes log n, and the memory consumption is order of log n. So that's how. And this how, these are the information we store in a particular node about all. And apart from this particular routing information, we also store our own files or something. Like the files will be stored. Let me explain about files later. Let's see how the routing works. Let's say you want to go to a particular, like you want to fetch a particular, and just let me clear this thing. So again, let's get it in the example of service.com. So let's say in this case, P10 want to know about service.com, the information about service.com thing. So this what it does is it finds the ID. Like how we find the ID, we can hash this particular meta, the service.com. It provides, let's say if you use SHA-1, it provides 128 and we truncate to M bits. In our case, we take first 8 bits. First 8 bits is provider, and when we convert it into a decimal, we get a number. So let's say the number represents 254. Let's say 254. The ID says 254. It doesn't know like whether the P10 doesn't know whether the 254 node is present or not. It just won't route along using its finger table. So it just has a finger table. Doesn't know about all the system in the node. It only knows the nodes in its own finger table. So what it does for routing, for routing, what it does, it looks up at the finger table. So it uses the ID, trying to find the best possible ID for it. Like it tries to find the highest possible ID, but less than the ID of the file. So in this case, it checks whether 50, it's a highest possible thing, but less than 254. Yeah, it is, and it checks the next node. Checks the next node, still 50. It still goes here, like 128. Yeah, still. It's best possible among all the other entries, but it's not. And it's still less than 254. It checks 200. Yeah, like it's less than 254 and it's the highest possible entry, and since it doesn't have any more requests, what it does, it forwards to 50, like it forwards to the P10 forwards the request to 250. Sorry, not 250, my bad. 200. It forwards the request to 200, like it wants a particular service.com file. So more like a sending a query message to 200. And what the 200 does, it has its own finger table entries. Again, it does the same thing, and it will be having a successor, like the 0th entry as 250 and one entry. So if you want to fill the particular table, 251, it's 250, and 2, it's 250, 3, and it's 250. 4, still 250. 5, 2 power 5. What is 2 power 5? Just 2 power 5, 16, 32. It's 250. For sixth entry, it will be obviously 0 because it will be greater 64. So 200 plus 64, 264 doesn't have 0. Then seventh entry is also, it's not 0, sorry. 128. It will add 64 plus 128. And it will be 10, I think so. Let it be. Like in this case, we don't want to worry about seventh entry. So what it does, it again does the same thing, like whether it checks the first entry, like whether it's lesser than 254, yes it is. And it still goes to the next entry, less than 254, yes it is. Comes till sixth entry, like sixth entry, checks whether it's less than 254. Since it's a circular linked list, like it will avoid looking into 0. So let's say, so 0 is considered greater than 255 here. So what it does, okay, then I shouldn't go beyond the sixth entry. It just checks the fifth entry and it forwards to 250, forwards the request to 250. And in this case, 250, what will do again? It checks its finger table, but it can't go beyond the successor. Like even its successor, zeroth entry is zero. I mean, it's f of f finger table entry, zeroth entry is zero itself. Like it checks, okay, uh, like the my successor itself, it's greater than particular ID we was searching for. So only the successor will be having the message. As I said, the successor will be containing all the thing. Like if the node is not present, the successor will be containing all the data. The 254th, I mean, the ID will be contained here. The 254, the particular service.com will be contained here. So it forwards the request to zero. Then in turn the zero, since the query could contain the message of contain the ID of P10, it directly speaks with P10, like or the it directly sends a request to P10 or something like that. Or we can have we can design our application as our, I mean, however we want. It's just the routing thing we want to worry about. The system provides the routing, like how it routes the request or how it sends the request. Those things are taken care here. So this is how code does the routing. And since we can see the routing is also O of log n, like they whenever a particular hop happens, the distance between the destination reduces by the half. So that what happens, like it entry is O, I mean the routing is O of log n. It is better than O of n. Then let's see how bootstrapping could happen. So in this case, the code, if you want to do bootstrapping in the code, let's say we want to introduce a new node to the system. What we do, we find the identify ID of the particular node. If you want to, let's say, be a new node, and when we sorry, when we hash, I mean, when we hash and mod, when we do truncate to m bits, its particular ID is 15. Let's say we get the P15, and somehow it was able to find, like it was able to get the address of P255. It communicates with P250. Sorry, 250. Sorry, it was able to get the address of 250. It will communicate with 250, and what it does, it uses a stabilization. I mean, code has its own, not its own. It uses a stabilization protocol to accommodate churns. Churns are nothing but leaving and joining, peers leaving and joining the system. So stabilization protocol, what it does, like the P15, again, the ID is 15. Like we try to find the node, the successor of 15, like which node contains the 15 ID 15, and it uses the routing, same routing mechanism, and we'll be able to find that P50 has, I mean, P50 is a successor of ID 15, and it will be able to the P15 will get the address of P50, like P50's address, and it will send the address to P50, and whatever data it contains, like 11, 12, 13, 14, those data, like hashes of those data, I mean, what to say, like let's say if you hash certain .coms, v1 v1.com, v2.com, and those hash come under 11, 12, 13, 14, and 15, and it will be, since there is no node between P10 and P50, those data will be would have been served by P50 earlier. Since now we introduced P15, then and P50 comes to know about this data, like introduction of new node, and it will send all the data which whose hash comes under these things, will be sent to map to P15. They will contain all these data, like 11, 12, not 11, 11, 12, 13, 14, and 15. These data will be sent here, and it will P15 will map its successor to P50, and in turn, the P50 will also maintain the link to the predecessor P10. Like in some cases we can have a node's predecessor as well. So what it will do, it will send a request to P10 to remap its successor to P15. So once P10 gets its message, it maps its successor to P15. So essentially a link is formed, P10 and P15. P50. Now the P15 has to fill its finger table entries. How it does is it gets the data of successor, like whatever data, the finger table entries of the successor. It uses that, like it will think, okay, only those nodes are present in the system, and it will map the finger table. I mean, it will populate its finger table entry using that. then it will get the figure table entries of those nodes and try to stabilize itself in the system. So that's how it does recursively. The stabilization thing will be done throughout. Like it will be done at the background. It's not happens when a node joins or leaves. The stabilization, let's say it's more like a repeated thing, like an infinite thing, will be done again every 2 seconds or 10 seconds, like depending on the system, like the rate of churn, etc. So that's how the stabilization things like fault tolerance and bootstrapping are done. So any doubt about routing and bootstrapping and fault tolerance in code? Okay, that means let me continue with Calypso. Like Calypso is also a structured. It's again a structured P2P system, and it's more of an interesting thing. Like let's say they have overcome the. They find okay. We need to reduce the routing to much less complexity instead of O of log n. O1 of n could be better, and we can store more number of information. Here, the code stores only log n of the data, like log n of log n information. The complexity is O of log n. N says number of systems and the number of nodes, expected nodes in the system. And since the memory, like we have abundant availability of memory, like we say 4 GB, like minimum we today we have systems with 8 GB memory. So we do have abundance of memory. Let's say we do trade off with like we can trade off the routing with memory. Let's have O of one routing, but O of log n memory. So that's what Caleb does. Like Caleb organizes the node into k different groups. Like these groups are called affinity groups. Affinity means like a similar group. Let's say affinity, more likely together or something like that. So they form their nodes into k different groups. K will be basically is equal to root of, I mean, almost equal to root of n. N is totally expected number of nodes in the system. So that's how, like, the system will be configured with the k to a set value, and they'll be expecting, okay, these much number of nodes will be present. That's how they start the system. And it's configurable as well. Like we can, if you want to implement our own implement, let's say we expect only less number of nodes in the system, we can reduce the k value, or more number of system, we can increase the k value. So what it does, we find the ID again using the same IP address and port. We hash the value and mod the value to k, like hash of the IP and mod to k. It will give the group ID, like which particular node will, I mean, which particular group the particular node represents or node joins. Let's say we know that, I mean, we get the ID and they will be mapped to the particular group. Again, the file also done using the same. We've hashed the file meta and mod to k, and we will get the particular group for the file. And let's say 0. Let's say we have 1, 2, 3, and k is equal to 4 in this case. And when you hash a particular file meta, like file name, I mean, in our case it's URLs. You hash a particular URL, you will be mapping this, let's say in this group on 3, and what you will do is service.com, let's say service.com, and sorry, service.com, and which node the particular which node you serve that service.com thing. Let's say this is the particular node. There its IP address will be stored here as well, and every node in this group will be having this tuple in its memory. So here every node in this particular group will have this tuple in its memory. So that's how we use it. So this particular data is replicated in every node in this group. And for regarding the routing thing, when we come to the routing, so let's say we have this k different groups, 0, 1, 2, and each node in a group will be connected to all the nodes in the same group. It will be connected to the all groups, and in other group they'll be connected to at least, I mean, they'll be connected to one node. So in this case, here, or something like this. So that's how they maintain the routing information, like more like information about the system, or that's it. So they will have all the data. Now, if you want to get the, I mean, each and every node maintains the same thing. Like here, it will be, this particular node will be connected to a different node in other group. So something like that. So as you can say, it's very random, or using the TTL or something like that, they could be connected. This how they maintain the routing information. Now we want to look up for a particular thing. And again, we'll be coming back to a service.com thing. And let's say this particular service.com, this particular nodes want to identify where this, I mean, want to get the data about service.com thing. What it does, it again hashes the thing, hashes the server data, service.com, and modes to the k. It will get the data, let's say in this case, k minus 1, sorry, it will be k minus 1. Let it say it gets k minus 1 as value. And what it does, it will be having a connection, like it will be having a connection to the particular any node in the k minus 1 group. What it sends the request to the particular node service or something like that. What it does, this node checks its memory, checks which node hosts service.com thing, and sends its IP address. Let's say in this case, this particular node hosts uh, hosts service.com value thing. Uses it provides this particular node provides this node address, and it sends back the data like IP address of the particular node, and again in turn it connects with the particular node, this node, and gets the data. That's how the lookup things. So in this case, since there is high in the P2P system, there is high rate of churning and high rate of faults. What it could, let's say this particular links fail, what it does is it tries to forward the routing through other node in the system. Let's say it sends the request to other node, which is connected in the same group. Since it will be connected with all the nodes in the group, it could choose any node which is near to it, which has less round trip time, and sends the packet to the particular node. Sorry, packet to here, and in turn this packet will be forwarded to the k minus 1 group, whichever this node has been connected to. Let's say here, uh, and this in turn, okay, and it will provide the data about which particular node hosts the service.com thing. And even if it is failed, if it has failed, it will try to connect with other node and somehow it tries to connect with the k minus 1 group, and it even can use other nodes in other groups to connect with k minus 1 group. So however it want, it could connect. Since it's independent of the number of nodes in the system, this particular routing is independent of the number of nodes in the system. It's of one routing. It has of one route. So that's how routing in Kelep occurs. And in the behind, they could use a gossip protocol or something to maintain the membership of the particular group or nodes in the other group. So how they will be connecting to a particular node. Let's say you get the IP address of a particular a node in the system. Let's say a new node, a PEN. It gets IP address of some node in the system. This node, particular node. Uh, they would have formed a gossip among all the nodes in their own system. It could get the data about the gossip network, like IP address and node. It could connect itself to the gossip network. Like how it connects is like since this node will be connected to all the nodes, it would have a hash to a particular let's say in this case 1, and this node would have been connected to any one node. Let me run these things. Oh, sorry, bootstrapping clips. Have a different thing. So let's say P of n you have, and this is 0, 1, 2, 1, k minus 1. And when you hash up IP address, it gets 1 more 2k, you get 1. Then it knows the address of this particular node. And what it will do, it will get the information of nodes in first group. Let's say this node would have been connected to any one node in the first group. It will try to get that information, gets connected to the particular node, and it tries to get the information of other nodes in the group from this, since it will be connected to all other nodes, and it will form the connection. This is how it forms the connection with all the nodes. So this is how Kelep works. Since I think it's already 354. Hole punching, like it's I mean, these are the systems I wanted to explain, like Napster, Nutella, Code, and Phillips. So basically, P2P system, this basic concentrate on how routing works, how they handle faults, and how they bootstrap nodes. This is how a system does. And applications could be wide range. Now I explained web services, and even you can have a key value storage if you want to, or something like that. Anyway, any application you can develop on the particular P2P system of your own choice. So since our network, let's say our internet is structured for more of a client service approach, not a peer-to-peer service. So there is some constraint we face when we deploy a P2P in this normal network thing that is called hole punch. Like you have to do hole punching, let's say, since we have NATs, network address translates, and we also sit behind the firewall. Uh, like those won't allow for request. I mean, any ingress network. I mean, ingress request. Like it won't allow any connection to happen to the particular client. It will only allow the client connection to go outside the network, not inside the network. So those constraints are there. Like for that system, use hole punching. So such things to overcome those limitations. So that's it. Time permitted, I would have explained hole punching. Like I still need to study about hole punching. Yeah. Doubts.